All right. So I'll get started, I guess, introducing myself and giving some context for what this talk is about. And maybe I should make it clear. I'm just going to be showing a PowerPoint. I'm not going to be actually doing anything physical. So I don't know why they put me here, but they did, and I'm happy to be here, and I'm really glad you guys are all here. I know there's a ton of interesting talks and things to go see, but I'll try to make this interesting and worth your while. My name is Bernardo Malfitano. On my day job is I work at Boeing. I'm a structures engineer. I do research into structural fatigue and damage tolerance and things like corrosion and delamination in the various processes by which airplanes age over time and deteriorate over time, and how you plan maintenance, as most of you guys know, to catch things before they're dangerous, that kind of thing. But I've always been an airplane geek. I'm a pilot. I have an RV6, and throughout my childhood and my teenage years, I had a lot of questions about airplanes. I mean, once you learn the very basics of how an airplane works, the wings make lift and the engines make thrust, right? You start wondering things like, why don't we have more electric airplanes? Or there are all these advantages to canard airplanes. Why aren't all airplanes canard airplanes? And why do small airplanes seem to have, why is it that propellers seem to be good for small airplanes and jets seem to be good for bigger airplanes? And, you have all these questions. And I went to college and studied engineering and found the answers to most of these questions that I had about why airplanes are designed the way they are and why different airplanes are different and why certain design features aren't as common as you think. But unfortunately, the answers to these questions are kind of locked away inside thick textbooks full of intimidating equations, right? But it's possible to explain most of the answers to most of these questions to, normal people who don't have engineering degrees and don't like to do calculus and so on. And so what I did is I basically created a course while I was still in college, which was kind of an airplanes 101 or airplanes for dummies or whatever you want to call it, where I explain why airplanes are designed the way they are and why different airplanes are different for non-engineers. And I've been teaching that class for a while now. I mean, that was, more than 10 years ago. And when I started working for Boeing, I started teaching the class at Boeing. There was a, huge demand for it because, Boeing's a huge company. And most people at Boeing aren't engineers. Most people at Boeing are, there's a lot of people at Boeing who are accountants and communications professionals and lawyers and HR and, you name it. And even the engineers at Boeing, I'm a structures engineer, so I work with civil engineers and material scientists and other people who are not airplane people at all, right? Who don't know the difference between a flap and an aileron unless you tell them, and that kind of thing, which is fine. They do their jobs great, but they really enjoy the chance to have an airplanes 101 class and to ask their questions about why do you always see this and why do you never see that? So this is kind of a super short, compressed version of that class where I answer some of the most common questions about why airplanes are designed the way they are. In a way, this is what I wish someone had told me when I was in high school, and so that I didn't have to dig through all the textbooks and take all the classes to find the answers to it. So I just collected a few questions that I thought were the ones that I had and the ones most people have, and I'll go through them. And it's definitely not going to take an hour and 15 minutes. I've done this in like half an hour, and I added a few bonus ones at the end, so it'll stretch it a little further. But just so you know, I plan on being done way early, and I hope that you guys can come up with some questions on your own or of your own that we can spend some time talking about. But this, so in a way, what I'm going to present here just kind of get us warmed up, and I hope you guys can think of more things we can talk about. So here are some of the questions I'll go over. In no particular order, and we'll just get started after I show you the list. How do winglets work? Why do most small airplanes have propellers and big airplanes have jet engines? Why do stealth airplanes have parallel straight edges and flattened fuselages and all those design features? The way they look, usually they're on the tail. Why don't we have supersonic transport airplanes anymore? Why are there so few electric or solar airplanes? What are the pros and cons of composite materials versus metals? Why do you always notice engines getting wider and wider, especially on commercial airplanes? The diameter seems to be getting bigger and bigger. And then some airliners have T-tails and high wings or engines on the tail, and some don't. And, how does that end up happening? And then when do you have to retire an airplane? And again, most of this is fairly commercial airplane centric, but some of it isn't. And why do we still not have flying cars? Although that's obviously one that a lot of people are talking about now. So I'll give you my twist on it. And I threw some bonus ones at the end. All right, so I'll just go ahead and jump in. And this is obviously informal and for fun. So if anyone has any questions or thoughts or anything, please feel free to interrupt me. Like I said, we have plenty of time. We're definitely going to get through this with plenty of time to spare. So how do winglets work? That's one question that I get pretty often in my class. I'm actually looking around wishing I had a prop, but, it doesn't, or a thing to show you, but it doesn't matter. All right, how do winglets work? The first step in understanding how winglets work is to realize that, as you guys know, there is high pressure air under the wing and low pressure air over the wing, and that's what causes lift and pulls the wing up. How those pressures are generated, we're not going to get into right now, but we can all agree to that. And that means that at the edge of the wing, you have high pressure right here and low pressure right here at the tip, and that means that some of the high pressure air spills around the tip onto the, onto the lower pressure area on top, and so you get a wingtip vortex, right? And most of you guys are probably familiar with that. One step further from that is that also generates a span-wise component to the flow, right? The airplane is going straight forward, so you think that the air is flowing over the wing from the leading edge straight to the leading edge, chord-wise, except that's not quite true. Especially at higher angles of attack where you have the more intense vortex, the vortex causes the air over the top of the wing to get pushed towards the fuselage a little bit. Those are the green arrows over there. And the air under the bottom of the wing to get basically sucked by the vortex away from the fuselage a little bit as it goes under the wing. So you get that span-wise flow. And what that means is that right at the wingtip, you have on the bottom of the wing, you have some air going outwards a little bit, and at the top of the wing, you have some air coming inwards a little bit, and it's circulating around like that at the edge. So what does the winglet do? What the winglet does is it takes some of that air that's coming into the wing diagonally and deflects it towards the back. Do you see that? And that way, because it deflects towards the back, it basically generates thrust. It pushes the airplane forward. Or another way to think about it that I think makes sense is the winglet works exactly the same as a sail on a sailboat. Right, let's say I'm on a sailboat, and let's say there's wind blowing from you towards me, and let's say that I want to go that way. Like, what do I do? What I would do, the sail's basically like a wing, so I'm going to deflect the wing at some angle of attack this way, so that it deflects air that way and generates lift that way, right? And I'll go that way. And there's also the interaction between the hull and the water, which I'm not going to get into, but the basic idea is that, the sail or the winglet will deflect air in one direction so that it pushes itself in another direction. So if you have the winglet deflecting, so that air's coming in kind of sideways, and the winglet pushes that air, kind of straightens out the flow and pushes it towards the back, that'll cause the winglet to be pushed forward. And so it reduces drag, but in a way it's almost like it generates thrust. And there's no reason why the winglet just has to be on top, right? On top you have air coming inwards, so you can push that towards the back. In the bottom of the wing, there's air going outwards, you can push that towards the back too, except then the winglet has to be curved the other way, right? So the top winglet is curved like this, and if you have a lower winglet, it has to go the other way because the air is coming from that direction rather than from this direction. And if I'm not mistaken, the Very Easy was the very first airplane that was designed from the start to have winglets. And and Bert Rutan knew this. Whitcomb had just published the paper that describes all this when the Very Easy was being designed. One more thing to talk to that's worth thinking about winglets is that they reduce the induced drag, the drag due to lift. And that's the kind of drag that if you have a wider wingspan, you see gliders with high aspect ratio wings, that they have less induced drag, less drag due to lift. And so the more wingspan you have, the less drag due to lift you have. Each 2 feet of wingspan gives you about the same reduction in drag as 1 foot of wingtip extension. So if you took those winglets and you just did this, you'd actually be better off. So why do airplanes have winglets? Why don't they just have, wingtip extensions? The main reason is that, you see winglets on commercial airplanes. The main reason commercial airplanes have winglets is that the gates are only a certain width, so if your wingspan is that much, you run out of room. The only place you can go is up. 737s have winglets because the gates are only so wide, and if the wings were bigger, they wouldn't fit at the terminal. Notice that Boeing makes 737s for the Navy, right, the P-8, and those don't have winglets, those have wingtip extensions, although that's for other reasons too. And so why do business jets have winglets? I think it's to look cool. I'm not really sure, but even I asked my aerodynamics professor this once at Stanford, and he said, I can't really see a good reason. They should just make the wing bigger. Although, on a more serious note, if you already have a wing that you started off with, adding a winglet requires a lot less modification and redesign and analysis and so on than extending the wing. You extend the wing, you're changing the loads, you're increasing the bending moment on the wing, so you have to beef up basically the whole wing. putting a winglet on is a relatively localized thing that doesn't take a lot of work. Like, it's practical to take an existing airplane and put a winglet on it. It's much, much less practical to take an existing airplane and extend the wingtip. So for reasons like that, winglets often make sense, and you see them on airplanes. But if you notice, for example, most newly built airplanes, like for example, I'm going to be, sorry for being a little Boeing centric, but the 787, the 747-8, and most of in the 767-400, and the P-8. So all these airplanes that Boeing has come up with relatively recently don't have winglets. They have the, wingtip extensions. So that's all I'll say about that. Yeah. Yeah. So why Bert put wings on it? Very easy. In that case, it's one, because you want to take advantage of this without having to make the wings any bigger than necessary. But two, because they double as vertical stabilizers, right? If you have a swept wing and the wing is all the way in the back of the airplane, then you could have a vertical stabilizer, and there's a velocity twin over there as a vertical stabilizer. Or you could take that area and put it on the wingtips. It's still about as effective as a vertical stabilizer, but you double dip and you also get that. So in the case of canard airplanes with the wings in the back, it makes a little extra sense. All right, any other thoughts or questions or anything? All right, so that's winglets. All right, so why do small airplanes have propellers and big airplanes have jet engines? Of course, that's, in general, there's a whole bunch of tiny little jets. Where are they? Basically right behind me. No, wait, over there. I'm getting disoriented. Yeah, there's a bunch of, Subsonics and BD-5Js just up there. But in general, most big airplanes have jets and most small airplanes have propellers. And the real way to think about this, it's a little less confusing, is that what's really true is that fast airplanes have jet engines and slow airplanes have propellers. The reality, and why is that? It's because propellers are very efficient at slow speeds and very inefficient at high speeds. That's really the reason. If you try to take a propeller airplane and make it go as fast as even just an airliner, you'd be wasting a lot of fuel. You have to burn a lot of fuel to get a propeller airplane to go that fast. But if you're going like 80 miles an hour, 100 miles an hour, even 200 miles an hour, the propeller is very efficient and you burn very little fuel. So in the end, it's not so much about the size of the airplane, it's just that there happens to be a correlation where slow airplanes tend to be smaller and fast airplanes tend to be bigger, although it's not perfect. But yeah, if your mission is going 100 or 200 miles an hour or less, propellers are going to be more fuel efficient. And if your mission is going, 500-600 miles an hour or more, jet engines are going to be more efficient. And then, in the middle, you can kind of go either way. Okay, so why is that? Why are propellers very efficient at slow speeds and very inefficient at high speeds? It's the following. So imagine a propeller going around and the airplane is moving forward through the air. Imagine the tip of that propeller blade. The tip of that propeller blade makes a corkscrew in the air, right? And on a humid day, you can even see the vortex condensing. You actually see that corkscrew. But the propeller tip makes a corkscrew through the air. If the airplane is going relatively slowly, that corkscrew is going to be pretty steep, right? It's going to go round and round and round and not go forward very much. Imagine a Piper Cub taking off or something. But if the airplane is going really fast, that corkscrew is going to be kind of, unwound, right? It's going to be less steep. It's going to be off vertical and closer to the horizontal. I'm talking about the slope of that line that the propeller tip makes. Does that make sense? So in a slow airplane, you have this, or when it's going slow, you have this. And when it's going fast, you have this, right? Okay, so let's get there step by step. Remember, the propeller blade is a wing that makes lift in the forwards direction, in the direction you want to go, right? So it's just a wing going around and around. If that wing is slicing the air, is coming down through the air almost vertically, like this, then it's going to make lift almost horizontally, right? The blade comes down this way, the lift goes that way, and it's the direction you want to go. But if the propeller blade is cutting the air kind of diagonally as a wing, then it's making lift that way. So the faster you go, the less of your lift component is forwards, and the more of your lift component is fighting you trying to spin the blade around and then just wasting engine torque, right? So not only do you actually have less thrust and less maximum thrust in the forwards direction the faster you go, but you also have more and more of that lift fighting your engine torque as you try to spin the propeller. So the drag of the propeller goes up, so to speak, even more than you would think just from the speed. And that's something you can't really get around. You can kind of twist your propeller and be smart and optimize it for slightly higher speeds. But once you get past, maybe 300 miles an hour at the very most, if you try to go any faster than that, you're really going to be fighting this harder and harder and harder. So, yeah. Yeah, so we talk about the altitude. That's a good point. As you go up higher, the air gets thinner and you have less drag. But your engine's also going to have a harder time making thrust. So it depends on how these things balance out. But the fact is, if you're going through the air at a certain speed, regardless of the air density, the propeller is going to be cutting the air through a certain angle. Or if you're going through the air at a certain speed and your RPM is a certain RPM, then the angle of that line the propeller blade is cutting the air through is going to be a given. So actually, if you slow down your RPM, if you have a constant speed prop and you slow down your RPM, you're actually bringing yourself deeper into this, losing a little bit of efficiency that way. Usually it's okay because your RPM goes down, your fuel burn goes down by that much. But my point is, as you go faster and faster, one way or another, you're going to encounter this, less vertical, more horizontal propeller problem. So you had a question first, then yeah. What's that? So most jet airplanes go at, most airliners go at 500 or 600 miles an hour, and of course fighters can go supersonic. In these little, subsonics, BD-5 kind of airplanes, they go, 2-ish hundred miles an hour, maybe 3. I guess they try to go for 3 the other afternoon at the air show. And the thing is, as they go slower and slower, they don't get more and more efficient. So a jet going slow is going to basically be burning extra fuel. It could be going fast, but it's not, due to low altitude or whatever. So the jets do tend to be... Oh, I see what you're saying. Yes, that's a good question. That's something that also people often ask in my class. Most big jets nowadays have a turbofan, right? If you look at the front of the engine, you see basically a propeller going around, and most of the air that goes through that opening in the front of the engine doesn't go through the core of the engine to burn fuel. It just gets blown by the fan, by the propeller. So a modern jet engine is basically a propeller in a tube. And so why doesn't the propeller in the tube have all these problems? Well, it does, but the difference is the tube. The inlet of the engine, if you look at the shape of that tube, it gets a little wider, so the airflow slows down and it comes in the inlet. So the fan is going through air that's hitting the fan more slowly than the air that's going by the sides of the airplane. So locally, the turbofan is dealing with slower air, so it doesn't have these problems as much, or until later. Does that make sense? That's definitely a very good question. And in my class, I spent an hour just talking about engines, and that's something to talk about. So someone back here had a question. Yes. So number of blades. Yeah. Right. So let's get into number of blades. That's a good question. If you're so the slower you're flying, and the higher your RPM, the more the steeper that corkscrew gets. The faster you're flying, and the lower your RPM, all other things being equal, the more unwound that corkscrew gets. Right. Now think about how if your corkscrew is like this is just one blade. The other blade is trying to sneak between these diagonal lines. There isn't a lot of room, and the other blade is trying to cut in here too. So each blade is basically very close to the influence of the other. And if you have a lot of blades, they're all basically in each other's, wash or each other's wake. But if you're going fast, or if your RPM is relatively low, then there's a lot of room between where each blade cuts the air for more blades to be in here and not really be in the wake of the other ones. So basically, the faster you're going to fly, and the lower your RPM, and your RPM basically has to do with the diameter of the propeller, right? Because the tips have to be a little bit below the speed of sound. So if you have a big propeller, if you're a Q400 or an A400 or you name your or C130, your RPM is going to be lower than if you're a Cub or a 172 or an RV or whatever. So those big airplanes go faster too. So for those big airplanes, so the C130 and the A400 and so on, it makes sense to have a lot of blades because they have very unwound corkscrews, right? The wake of each blade is pretty far apart and there's room for more. But for a smaller propeller with more RPM in an airplane that flies more slowly, you probably want fewer blades. So in general, you probably want 2 blades in your Cub or in your 172, and you probably want a whole lot of blades in your C130 or your E2 or whatever. And there's exceptions, and I know that a lot of RVs have 3 or 4 bladed propellers and so on. But that's a general idea. Yeah. Yeah, I don't know if you guys have seen this, but there are at least pictures. I almost don't want to believe that they're real. Maybe some of you have actually seen this in real life, of a Piper Cub propeller that has 1 blade and a counterweight. And I have a hard time imagining that doesn't wobble itself apart, but apparently it's doable. I don't know, but yeah. But the higher the RPM and the slower you're going to fly, the fewer blades are optimal. So yeah, so I don't want to get into whether or not the one-bladed Piper Cub propeller is really the best solution, but that is something I've seen on the internet, right? So who knows? Yeah. Any other thoughts on propellers? And of course, here's the thing too, and I say this when I teach my class, each of these topics you could have a whole college course about, right? So I'm just barely scratching the surface and saying, oh, here's how we start to think about this. All right. So to totally change the topic, let's talk about stealth airplanes. And you know what stealth airplanes look like, right? We're going to have F-22s and F-35s used pretty soon, and you're seeing B-2s and so on. Why do they look that way? So to understand where that geometry comes from, you have to think a little bit about how light bounces off of shiny things, right? And if something is shiny, like say the screen, if a light ray hits the surface, the shiny surface, it'll bounce pretty much at the same angle that it came in, but the other way around. Just like a ball. If you throw a ball at a wall, it'll bounce at an angle. The angle on this side of the bounce is the same as the angle on that side of the bounce. And the same is true for light on a shiny surface. So for example, if you pick up, so what we have to think about here is, okay, what are the kinds of surfaces where you can see your reflection in the surface? If you're seeing your reflection in a surface, like in a mirror or anything that's shiny, if I pick this up and kind of see my reflection in, that means that there are photons going from your face to the thing and back to your face, right? If you're seeing your reflection. And, that's how radar works. So if you pick up a Christmas ornament or any kind of round thing like that, round shiny ball, you'll notice that at any angle that you turn the Christmas ornament, you're going to see a reflection of your face right in the middle. And why is that? It's because the surface of the round thing right in the middle is perpendicular to that line that the photon's going to make from your face to the thing back to your face. If you imagine the line of a photon that goes from your eye, that hits the Christmas ornament, and goes back towards your eye, if that's the angle, then that surface has to be at 90 degrees to that photon. And the middle of the sphere is exactly at 90 degrees to that light. Right? The light that goes from your face to the top of the ball kind of, bounces off that way. And the light that goes from your face to kind of the, upper-ish corner side of the ball will bounce off this way. But it's the light that goes right to the middle that's going to bounce straight back and back into your eye. Right? And that's where you're going to see your reflection. And that's because the thing is round. Right? Because round things reflect light in every direction. Right? As light hits the round thing from here, some of it bounces straight back, some of it bounces this way, some of it barely bounces at all, right? Light goes everywhere if you have a round thing. But a flattened thing, if you imagine a spoon or a mirror, there's only a relatively narrow range of angles that you can see your reflection in a mirror, right? So for me to see my reflection here, I have to basically stand right here and look this way, right? From here, I can't see my reflection on the screen because all the photons from my face will hit the screen and go off that way, all right? And so you start to think about, well, if I want to design an airplane such that all the radar photons hit the airplane and bounce away from the radar, not back to the radar, right, so the airplane's stealthy, you're going to end up wanting all of the surfaces of the airplane to be relatively flat and ideally sloped away from the sides where the radar is going to come from, right? Or another way to think about it, let's say you have a round fuselage or a flattened fuselage. If you have a rounded fuselage and I shoot some radar at it, the photons of radar that are going to go back to the radar are the ones that hit the vertical sides here, right? The photons that hit the belly of the airplane are going to bounce off that way. The photons that hit the top of the airplane are going to bounce off that way. It's really that vertical-ish middle is what you're going to see on the radar's going to see. That the photons are going to bounce back to the radar. So if you just get rid of that vertical middle, or if you kind of stretch it out like this, then the photons are going to bounce up and down, and not as many of them will come back towards the radar. So you can imagine, the chines on an SR-71, or the kind of flattened fuselage of like an F-117 or a B-2, or even the F-22, has enough of a little edge and slopes to it so that most of the radar will bounce in some direction other than straight back the way it came. Right? You're getting rid of those vertical sides that are the real problem. So that starts to explain why you want a flattened fuselage. It doesn't have to be flat facets like the F-117. It can just be relatively flat. And actually during flight testing in the 40s of the, the B-37 and the B-49 are the Northrop Flying Wings, and I've heard of this about the Avro Vulcan too, they're all basically flat airplanes with, tiny little tail fins. Sometimes they'll disappear from the radar screen. And they weren't even trying to be stealthy, they're just trying to see how a flying wings without tails work. So they became kind of accidentally stealthy just from being flat enough to use this effect. So that's one aspect of it. Another thing you notice about stealth airplanes is that they have these sharp, these straight line edges, and a lot of times these straight line edges are grouped, right? For example, these edges and all the red edges are parallel, and all the blue edges are parallel, and all the green edges are parallel. And why is that? And the B2 is a really obvious example of that. Why are the edges aligned? The edges are aligned because, if you think about, again, me shooting radar at the edge of this airplane, the radar is going to bounce basically, at the same angle it came in. So from which direction, let's say I take a, generic stealth fighter kind of planform like that, and I put it over here. From which directions am I going to shoot radar at it and get the radar straight back? The directions are what's marked by these kind of color bands here. For example, if I'm in the red zone here, and I shoot radar at let's say the F-22, it'll hit the edge at a 90-degree angle and go back the way it came, and the radar's going to pick it up. But if the radar is here in the white zone and it shoots radar at the F-22, some of it's going to bounce off that way, some of it's going to bounce off that way, right? So if all the edges are aligned, then there are only a few narrow bands of directions that are at 90 degrees to some edge. And so from these directions, you're going to get a lot of radar back. But if you're somewhere in between, even from the edges, most of the photons will bounce away from the way they came. And that's why you get aligned edges like that. Does that make sense? And then one last thing about stealth airplanes, right? If you have two reflective surfaces at 90 degrees, or even 3 if you have half a cube, any photon that comes in will go out straight the way it came. So if, I can prove this to you like right here. If you have a 90 degree, two mirrors like this, and light comes in relatively steeply, it'll bounce off this way, which is 180 minus that, and then it'll bounce off that way, which is 180 minus that. So it's 180 minus 180 minus that, which means the light's going to go straight back the same angle that it came. You can do the math if you want, but just graphically kind of makes sense, right? If the light hits it from kind of down here, it'll bounce at like 45 degrees. It'll bounce at 45 degrees, go straight back the way it came. If the light hits it from a shallow angle, it'll bounce at a steep angle here, shallow angle here, go straight back the way it came. So if you have two things at 90 degrees, no matter which way the light's coming from, it's going to go back the way it came, right? If you have two mirrors at 90 degrees like this, as you walk and you look at that corner, you see your reflection kind of stuck in the corner of the mirror. Have you ever seen that, like at a store window or something? That's that same effect. And if you look at people who do land surveying with lasers and stuff, they have these, they have a tripod with a thing on top that looks like a bunch of little mirrors, and it's 3 sides of a cube that use that effect to make sure the laser goes exactly back the way it came. So those are called retroreflectors. Right, so if you have two surfaces at 90 degrees, you get a retroreflector, and all the photons go straight back the way they came. So non-stealthy airplanes have a lot of 90-degree angles, right? A lot of 90-degree tail fins and wings and rectangular air intakes and so on, plus a bunch of circles. Right? You talked about why circles are bad, because circles reflect light everywhere. But stealthy airplanes tend to avoid 90-degree angles to not send the photons back the way they came, right? To not send the radar back to where it came from. So you end up with these parallelogram-shaped intakes and canted tail fins and all that kind of stuff. So that's where the no right angles idea comes from, because you don't want a retroreflector. All right, any other questions or thoughts or anything about stealth airplanes? And I'll totally change the topic again. Yes.
The slide before where you're talking about all the angles are the same.
Yeah.
Doesn't that concentrate the possibility of detecting that damage in areas?
So the radar reflectivity of the airplane is very high inside these bands. But here's the thing, the airplane's flying, and so those bands are moving. So the radar is only inside the band for a fraction of a second. Unless a fighter is somehow hanging out in that band, which I guess is possible, but it's still pretty unlikely that you're going to be pretty safe. All right, any other thoughts? All right, so we'll keep going. Next one, supersonic transports. That's something that people often ask in the class. So now there's more and more research in this area. So now more people are becoming more educated about this. In the late 60s, the Concorde started flying. And through the 70s, 80s, 90s, the Concorde offered supersonic commercial transportation. You could buy a Concorde ticket and fly between New York and London or Paris and a few other places at way more than twice the speed of a normal airliner. And then they stopped, which seems kind of a backwards move in technology. And why is that? And are we going to get back to it? So there's two main reasons. One that you'll hear about as you'll talk to supersonic transport people here. I'll get to that in a second. The main reason is that it was expensive. So even before people worried about sonic booms, or even if you're just flying over the ocean, if you go that fast, you're going to burn more fuel. There's no way around it. Like a Concorde ticket is always going to be more expensive, or some kind of supersonic transport ticket is always going to be more expensive than going at less than the speed of sound, just because there's a lot more drag and you're going to burn a lot more fuel. And there's ways to overcome that if you're really smart, but you can't totally eliminate it. It's going to be more expensive, right? So the number of people willing to spend a little bit more for an airplane ticket to go faster is pretty small. It's kind of a 1%er kind of thing. And most of the people who fly the Concorde now flying business jets, which are better at point-to-point transportation. So the market's very small, right? They only build 20 Concordes or 22 or something, right? How many, 67s and 87s and 737s and A320s and A330s are being built? Hundreds and hundreds. So the market's very small. So if a company says, I'm going to develop a commercial supersonic transport, they're going to spend billions of dollars developing it and then sell 20 of them, right? So each one's going to cost, $1 billion or something. So that's not going to pay for itself is really the bottom line. But with, like I said, most of the people who flew Concordes now fly business jets. Couldn't you make a supersonic business jet? And yeah, maybe you could. There would be a market for that. And so throughout these decades, a lot of companies, including like Tupolev and Gulfstream and Sukhoi and and the more obvious ones, have looked into making supersonic business jets. And then the problem that comes up, saying, okay, let's say we make a supersonic business jet, is that airplanes going supersonic make shockwaves. They make a sonic boom, and that shockwave is intense enough to break windows on the ground. And for that reason, supersonic flight over the continental U.S. is illegal. And so the only way that you would be allowed to have a supersonic transport airplane over the U.S. is if you somehow shaped it such that it didn't make a boom that's strong enough to break the windows on the ground when it flies over. And a lot of research over a lot of the past several years has been done to try to figure that out. So Gulfstream partnered with NASA, I want to say like 15-ish years ago, and looked into how to mitigate that boom. So they had what they called a quiet spike F-15. They had a big telescoping spike out the nose to see if they could push the air aside a little more gradually. And they had the F-5 shaped boom demonstrator, where they tried to shape the fuselage in such a way that it didn't push the air out of the way too abruptly, and and then the in wave of pressure that the airplane makes doesn't, or the pressure waves don't coalesce into an end that gives you a sharp boom. There's a NASA pavilion over there where I'm sure they can tell you in more detail how they try to suppress the boom. But it's looking pretty promising. So the next step is, if probably again in the NASA pavilion, there's people in the Quest program, the X-59 program, that are going to fly an airplane to try to test these ideas. Of the whole airplane, the point of the airplane is to be designed around a low sonic boom, more of a sonic woof or a sonic thump or something like that. And here it is being wind tunnel tested, and it's being built. And so there are companies trying to jump in on this and say, okay, well then if all this works out, we want to use this technology and make a supersonic business jet. So Ariane is arguably the most famous, and there are others. There's Spike. There's a company called Boom that wants to go back to making supersonic transports. They think that it's doable. They're making a small demonstrator too. So there's a decent chance that there may be supersonic business jets in the future. There's some small chance of us getting back to supersonic airliners, but the bottom line is, even if we do, if we figure out the boom thing, it is going to be expensive. It's going to cost quite a bit more than your normal ticket on a 37 or A320 or something. Yeah, so that's all I have to say about supersonic transports. Any questions or thoughts? All right, yes. It continues. Once the airplane is going supersonic, it's basically making a cone-shaped pressure wave, or multiple concentric cone-shaped pressure waves around it. And as the airplane flies, if you imagine a cone coming from the back of the airplane, that cone hits the ground in a parabola, and that wave on the ground is a sonic boom that's traveling under the airplane the whole time it's supersonic. So yeah, so you get the boom all the way.
About 3 times more expensive.
Yeah, so how much more expensive would it be? It depends how much higher the drag is. That's one part of it. And depending on how you shape the fuselage and how smooth your surfaces are and so on, you'll get a different answer. And it depends on how efficient the engines are, because you might think, if you're going really fast, your engine's going to be a lower bypass engine. It's going to be a narrower fan, so you're going to lose that. Actually, I haven't talked about that yet, but the engine's going to be less efficient just because it has to be kind of narrower, and I'll explain why in a second. But some of the engine thermal efficiency, the thermodynamic efficiency, has to do with how much the engine compresses the air, right? All those compressors in the front of a jet engine and the piston in your piston engine compress the air because when you combust fuel, the more compressed the air is, the more of the energy from the combustion you can harness as work. And if you're going really, the faster you're going, the more ram pressure, imagine like a pitot tube, right? The higher the pressure just from the air slowing down and going into the engine. So you basically get free pressure and free efficiency when you go faster. So it's conceivable that the inefficiency or the loss in efficiency from the narrower fan could be at least partially offset by going faster and getting more free pressure, free ram pressure from slowing down the air. So it basically depends on you know, what's the drag in the airplane going to be and so on. So it depends on everything. So I wouldn't be able to tell you how many times more expensive. But if you look back at the Concorde era, you know, I think it was in the order of 10 times more expensive. So nowadays it could probably be less than that, but that's still the kind of number we're talking about. Probably several times. I think if they can get it down to 3 times, they'll be really happy. But, that's just a guess. All right, so supersonic transports. What else is on the list? Oh, right, electric and solar airplanes. Yeah, if you walk around here nowadays, you'll see all these different electric, not just airplanes, but also vertical takeoff and landing things, you know, being invented. And you might say, so you might wonder, oh, why haven't we had electric airplanes up until now? Oh, it's because the technology wasn't around or people hasn't invented it. And that's not really true. The first electric airplane was from the 70s, right? You can't really see what this is, but it's a little piece of paper about the first electric airplane, and it's from 73, I want to say. So technology's been around, electric motors have been around forever. So I'll tell you what the main problem is with electric airplanes that's now being overcome. The main problem with electric airplanes is that, you've probably heard other people say this if you go to these booths, is that the energy density of batteries is relatively low compared to fuel, right? So for example, when you fill up your gas tank, say you're driving your car, and you go to a gas station and you get gas, how many pounds of gas do you get, right? So each gallon weighs about 6 pounds, right, like in an airplane. And so if you get 15, 16, 20 gallons, you're probably getting 70, 90, 100 and some pounds, give or take, right? So 100 pounds of gas. How much does a Tesla battery weigh? Carries about the same amount of energy as a gas tank. Anyone know? Yeah, it's more than 1,000 pounds. It's like 1,300, 1,400 pounds. And what that tells you is that a pound of gas, a pound of fuel, holds about 15 times as much energy as a pound of a battery. So imagine an airplane. If you went to an airplane and you just took out the fuel and replaced it with batteries of about the same weight, you now have 6 or 7% as much energy as you just did, right? Which means you're either not going to fly very fast, or you're going to not fly for very long. And of course, you can try to offset this by having a really efficient airplane and low drag and optimize it for flying slowly. But the bottom line is you're not going to get the kind of range that you would get for a fuel-powered airplane. And again, as batteries get better and as the airplanes are optimized to have batteries, we're now getting to the point where you can go flying for maybe a couple hours. But it's still not going to give you the kind of performance that the fuel will give you. And for a few uses, this already makes sense, right? There's a lot of electric ultralights. You know, ultralight people don't go flying for hours and hours, so they're fine. There's a lot of electric motor gliders, right? So a motor glider just needs to be able to carry you to where the lift is, and then you can go soaring, right? So if you have 20 minutes in a motor glider, that might be good enough. So there's a lot of electric ultralights and electric motor gliders. You know, and now Pipistrel's here. They have an electric, trainer. You know, if you think about most training flights, they're about an hour long, and you land back to the same place you started. So if you can't fly for hours and hours, it's fine. But there are companies out there trying to go even further. Right? The one that I think is most interesting is one called Zunum, and they're in the Seattle area, and Boeing's actually starting to work with them. And they're proposing to make electric or hybrid electric small transport airplanes. And I think that they're planning, I have to go to their website and see the details, but I think their plan is to start off with like a 12-seater charter flight kind of airplane that is both fuel-powered and electric-powered. And once that gets into service and they work out the kinks, they can see if they want to make something bigger. So the only problem is really range, right? You're not going to fly to Europe in an electric airplane, but if you're doing relatively small local flights, the kind of flights you do now in turboprops or regional jets, you could do an electric airplane. So yes, but the main problem is range because of the low energy density. But then you might say, hey, why don't we make a solar-powered airplane? If you have solar cells on top of the airplane, you pick up the energy as you go, and you don't have to carry the heavy batteries around. And that's true, except sunlight only delivers so much power, right? Each square foot of solar cell can only generate so many watts of power, even on a sunny day. And if you think about a square foot of solar cell generating a certain number of watts, as you go faster and faster and faster and faster, the drag on that square foot gets higher and higher and higher. And at some speed, the power that you're making from the sun is the same as the power that you need just to pull it through the air. So there's basically a strict speed limit on solar-powered airplanes, and you can't go any faster because there's just not enough power in sunlight. And that limit depends how you do the calculation, but it's less than 100 miles an hour, so it's not very fast. But then here's the thing: you don't cover the whole airplane with solar cells, right? Just the top. And you probably want to save a little bit of power that you're making while you're flying. It's like if you want to fly overnight and stuff, you don't want to use up all the power you're making. So in practice, a true practical speed for a solar-powered airplane like all of these is like 25, 35 miles an hour. Right? So for example, NASA made the Helios, which is the highest flying airplane ever, flew higher than the Blackbird, 90-some thousand feet, and yeah, 25, 30 miles an hour. Right? The what's called the Solar Impulse flew all the way around the world, making a lot of stops at 25, 30 miles an hour. And you guys have probably flown into 30 mile an hour headwinds, right? If you have a 30 mile an hour headwind, you're not going to go anywhere in these airplanes. Actually, the longest leg that the Solar Impulse made in its hops around the world was from Japan to Hawaii, and that particular flight set a bunch of records because of how slow it was. It was the longest solo flight ever. It was 5 days and then something, and the longest flight in an electric or solar airplane and so on because they went from Japan to Hawaii at 25 miles an hour. But that still that has some uses, right? So for example, there's a group in Europe that's making solar-powered gliders, and gliders are perfectly happy to fly at 30 miles an hour if you design them just right. So if you make a so solar motor glider, totally makes sense. So they have the motor gliders called the Sunseekers, which are pretty good, and there are companies making solar-powered UAVs, right? A solar-powered UAV for certain uses of UAVs, like if you want to just have a camera on a UAV and look down and see what's happening on the ground, or for military applications, if you want to basically, if you have a bomb or some kind of weapon, and you just want to stay there for a while until the bad guys show up, and then you go and attack them, or something like that. That makes all kinds of sense. You don't need to go fast. You just need to stay up in the air and not land. And so this one that I'm showing here is called the Zephyr, made by Kinetic, and they've flown it for 2 weeks nonstop. And conceivably, you could fly this airplane for months nonstop. You can just hang out there. And it's basically like, it does all the things that satellites do, except it's cheaper. You don't need a rocket to put this in space, and it's closer to the ground, which is good for cameras and relaying communication signals and that kind of thing. So you basically have an in-atmosphere satellite if you make a solar-powered drone, and that's kind of cool. So there are uses for this, and it is a technology that's pretty exciting. But for transportation, at 30 miles an hour, I don't know. But that's generally how that works. Any thoughts or questions about electric airplanes? And I'm not an expert in this. I'm just trying to watch the industry and do some very basic physics. There are experts in electric airplanes around here at Oshkosh this week if you want to go talk to them. All right. So composites and metals, that's another question that I get a lot. A lot of people just say, oh, composites are better than metals. Or people say, oh, there's times when they are and times when they aren't. Or, why are they better anyways? Are they really just that much lighter? So here's what I say when I teach my course about airplane design. It's basically just pros and cons, right? So what are the pros of composites? One, they're lighter. And two, and this is kind of the most interesting one that a lot of people don't really appreciate, they're tailorable. And what that means is a composite is a laminate, right? That means there's just lots of layers of fiberglass or carbon fiber. And each of those layers has all the fibers going along a certain direction. So for example, I could take a tool and lay down fiberglass or carbon fiber and have all the fibers going, for example, put one layer down with the fibers going this way, let's call this 0 degrees, and then one layer with all the fibers going this way, let's call that 90 degrees, and then another layer with 45, and another one with minus 45, or biaxial or whatever. So let's say I do 0, 90, 45, minus 45, and I do a few groups of 4 layers in these 4, different directions, 45 degrees apart. What I end up with is something that's, about as strong as aluminum and a little bit lighter, or a little bit heavier if it's fiberglass, but it's generally comparable. Now here's the exciting part. Let's say I'm making a lower wing skin. The lower wing skin, the wing bends up in flight. The lower wing skin is in tension along the wingspan, so it's only really loaded along the wingspan. There aren't really a whole lot of loads in the forward and aft direction on the wing skin. So I can basically take my fiberglass or my carbon fiber and take out most of the fibers that go this way, or most of the fibers that go at 45 degrees, and leave, not only fibers that go along the wingspan, but mostly fibers that go along the wingspan. A few more fibers I'll leave in there to kind of hold it all together. But for the most part, I can just have fibers going this way. And if I do that, I remove a whole bunch of the weight. I can take out like half the weight of the fibers that go in the other directions, but I still retain 100% of my strength, or close to it, in this direction. So the composite can be much stronger in one direction and not as strong in the other direction, and you can take out the weight, but you still have the strength that you need in the direction you need. Right? So by tailoring what fraction of the fibers go in what direction, I can make the material stronger or less strong in the different directions depending on the loads, and then I don't have material that's sitting there being strong in a direction that I don't need. So that's kind of the main. So just doing that, you can save a whole lot of weight. The other advantage, and I don't know how many of you guys have EZs or Glaciers or Lanciers or other composite airplanes, is less maintenance. So composites don't really corrode, and they don't really fatigue crack. They do have their own problems. They do deteriorate over time. Like I said, that's kind of what I do for a living, is think about that side of things. But in general, overall, you would expect that a composite airplane the composite structure will give you fewer maintenance headaches and costs over the life of the airplane than a metal one. Okay, so what are the disadvantages? The main disadvantage of composites is that composites are relatively weak in the through the thickness direction, right? So they may be very strong, in the plane like this, but once I start loading it in this direction, they come apart pretty easily. They may have, 5 to 10% of the strength, something like that, between the layers. And here's where this gets really tricky. Whenever you take any piece of material and you bend it, there are small forces that are going to push through the thickness, trying to push the surfaces apart, right? If you can see that if you take a stack of paper, like a phone book or just a stack of papers, and you hold the ends together so they don't slip, and you try to bend it, you're going to see this happen. It'll buckle. It'll basically come apart like that. So what that means is that there are very small forces trying to push the surfaces apart of something when you're bending it. And these are called secondary loads. There's different names for them. There's different textbooks that talk about how to calculate them. But the point is, for metal or even wood, you don't really worry about this too much because these are very small forces. They're only about 5% of the stresses on the surface going along the surface. But if you have a laminate and the strength of the laminate through the thickness is only 5 or 10% of the strength along the surface, then that might be what gets you, right? You might be bending your spar or whatever it is, and it may delaminate like that rather than ripping at the surface the way aluminum would, rather than breaking at the surface. So that's a whole different failure mode that when you're analyzing and figuring out the strength of your composite structure, you have to check. And it's a little counterintuitive for people who have worked their whole lives with materials that are not laminates. It's something that's not intuitive and they have to get used to. But that's another failure mode to worry about, I guess is what I'm saying. And there's other small disadvantages too, like they're not as good at high temperature. Your firewall forward, or if you have an EZ, your firewall aft, is not going to be all fiberglass and foam. And another disadvantage is cost. And actually, up until 10 or so years ago, a little more than that, maybe 15 years ago, they were so expensive that they weren't really practical for, carbon fiber was so expensive that it wasn't really practical for commercial aviation, right? I mean, we had carbon fiber technology in the 80s, right? The Voyager flew in the 80s around the world, and the B-2 flew in the 80s, and the V-22 flew in the 80s. That's mostly carbon fiber. And the Boeing Condor, there's all kinds of military airplanes and weird one-offs that flew in the 80s with carbon fiber. But it all costs a fortune, right? The B-2 is the most expensive airplane ever built. We made Boeing made the 777 mostly out of aluminum, and there's quite a bit of composite in there. Boeing could have made the whole 777 out of carbon fiber, but then it would have cost as much as the B-2, right? Then they wouldn't have sold it. So up until the price started coming down, it wasn't really practical for mass production, commercial applications, and so on. So that's one big disadvantage is the cost. And it's not that expensive anymore, but it's carbon fiber, but it's still pretty expensive. And then there's damage tolerance and fatigue characteristics that I don't want to get into. But basically, you have to build composite structure with more, beefier, with more margin, with more excess spare capability than metallic structure. You need a lot of material. When you build composite structure, if you do it right, you need a lot of material there, kind of just in case, right? In case there are delaminations or in case you mess something up and you can't see it, you need some extra material there just to hold it all together. So that eats away at some of the, the bit higher strength, lower weight, and so on that I was talking about. And the specific application for that, or the specific problem that gives you, is for very thin structure. So some airplanes have very thin skins. It's hard to make a composite one as light as an aluminum one, because a composite one, you would start off making very thin, but then you need all that extra material, and you end up with something that's heavier than aluminum. So for some thin structure, it doesn't really work out. But anyways, again, as with all these things I'm talking about, you can take multiple college courses covering all these little details and learn how to do the calculations. That's just some of the things we worry about. All right, any questions or thoughts or anything? Right. And again, if you think of one, or if you think of something about something I said earlier, feel free to stop me. All right, so wider engines. Why do you notice that jet engines keep getting wider and wider? Why is it better that they're wider? And the same thing's true of propellers. Why do you want the widest diameter propeller possible, right? Most of you guys probably know that the Corsair has that weird kink in the wing, so that basically to given a certain size of landing gear, to lift the engine up higher in the air, so the propeller could be wider. So why are wider turbofan engines like this and wider propellers more fuel efficient? Or why did they allow the engine to be more fuel efficient? And the way I explained it is the following. This bullet is slightly weird, but anyways, what you want out of an engine is thrust force, right? You want the engine to push the airplane forwards through the air. And thrust force, and this gets a little bit into Newtonian physics, but it's not that complicated. Thrust force is how much momentum you're giving to the air. So how much mv you're giving to the air. So the m is the mass of air, how many pounds of air the engine is pushing backwards every second. And the v is how much speed you're giving to the air, right? So the air comes in relatively slowly and goes out the back relatively quickly. So how much air are you interacting with per second? And how much speed are you giving to the air? That tells you, multiply those together, that tells you the thrust force of the engine. So that's what you want. What you pay is power, is energy, is fuel burn. And the power, the energy, the fuel burn, has to do with how much kinetic energy you give to the air. Right? So the thrust force is how much momentum you're giving to the air. That's the formula. The fuel burn and the power and the energy is how much kinetic energy you're giving to the air. And that's 1/2 mv squared. Right? So you can start to see that, well, if I want a certain amount of thrust, I can have more or less mass, more or less velocity, and I get the thrust that I need. But if my mass goes up a little bit and my velocity goes down a little bit, I might have the same thrust, but my power is going to go down disproportionately because it's v squared in the formula. Right? So more m. For example, let's say I take an engine, like a jet engine, and I make it 40% wider. So it goes from 10 feet to 14 feet. That's a little too much, but something like that. It goes from 1 foot to 1.4 feet. So I made it 40% wider. If you make it 40% wider, the area of that circle goes up by 2, right? Because it's 1.4 times 1.4. So the area goes up by 2. So I'm now influencing twice as much air. I'm swallowing twice as much air, so to speak. If I'm swallowing twice as much air, I could push it out the back with half the added speed and still get the thrust that I need, same thrust, but my 1/2 mv squared, this goes up by 2, this goes down by 4, because it's squared, so I only need half the power, right? And this is a bit of an oversimplification, there's a lot of other factors too, but just from looking at these two very simple formulas, you start to get an idea that what you really want is to move more air, more m, and give it less extra energy, less v, right? The higher your m is and the lower your v is, the more efficient your energy is going to be. And you accomplish that by just making it wider. So you make it as wide as you can within various constraints, like the structure of the fan blades and making the tips not supersonic and all that kind of stuff. But generally, you want it to be as wide as you can. To the extent that like a lot of World War II airplanes with those really big engines and really big propellers had reduction gear, right? So they can make the propellers even bigger without the tips going supersonic. And that ended up paying for itself. Yeah, does that make sense? Are there any questions? Yeah, and again, this is kind of a it's more complicated than that, but that's kind of the main factor that goes in. And then something else people always ask me about. Again, I mostly teach this class inside Boeing, so it's mostly commercial airplane people. I live in Seattle. So people ask, why do some airliners and some airplanes have T-tails, but a lot of them don't? And why do some airplanes have high wings, but Boeing keeps making airplanes, and Airbus keeps making airplanes with low wings? And sometimes the engines go in the tail. For some airplanes, like an MD-80 or a Learjet, the engines go in the tail, but most airplanes don't. So what are some reasons why sometimes that makes sense and sometimes it doesn't? So I'll give you a few things to think about. There's a lot of pros and cons. Most of the airplanes that have a T-tail, and there's some exceptions, but most of the airplanes that have a T-tail to get the horizontal stabilizer out of the way of the jet wash, right? So you have engines. If your engines are down low in an airliner, you can have a horizontal stabilizer on the tail cone. But if your engines get higher because you have high wings or because you have the engines in the tail, then you want to move the horizontal stabilizer out from behind the engines, and you end up with a T-tail. So that's usually the main reason why you see them do that. And there are exceptions, right? The B-52 doesn't have a T-tail, and the Antonov 124 don't. But in general, that's what you get. There's some other advantages too, like if you have a normal horizontal stabilizer is in the wake of the airplane, so the air that's hitting it is slower and more turbulent. If you put the horizontal stabilizers up in the fresh air, then the air hit going by them is faster, and you can have a smaller horizontal stabilizer. It'll still be as effective, so less drag. But there's a few disadvantages. Obviously, you have to make your vertical stabilizer much stronger and heavier to be able to keep the horizontal up on top. And then there's a possibility of a deep stall, right? If you stall the airplane, if you stall the wings at a high angle of attack, if the wake of the stalled wings hit the horizontal stabilizer, you may lose elevator effectiveness and get stuck in the stall. And there was an infamous British airliner crash in the 60s where this happened, and the test flight crew died. So this is something you really need to be careful about. Let's see what else. And then high wings. Why do we have low wings and high wings? The advantages of high wings, airplanes that have high wings, a lot of the times it's for one of two reasons. One is that they're less prone to ingest FOD, right? If you're operating off of unprepared airstrips, if you're landing, C-17s and things out in the desert, and you're kicking up a lot of dust, you probably want your engines higher up off the ground. And that's also good for propeller airplanes, because if your wing is higher up off the ground, the propeller can be wider and not hit the ground. So a lot of turboprops with really big propellers, it makes sense to have the high wing just to keep the engine higher off the ground. So again, same thing as a Corsair, right? You just want the engine high up off the ground. But there are a few disadvantages. So there's a few reasons you don't see this a lot in airliners. One disadvantage is that if your wing is down low, then it's easier to put your landing gear in there. But if your engine is up high, then you have to put your landing gear in like little pods or something, and that adds weight and that adds drag. Or you can put your engines on the wing, but then you have to have these, or your landing gear on the wings, but then you have these super tall landing gear that are also going to be very heavy. So you don't want that if you can avoid it. And there's a few other things too, like airliners have ditching requirements, right? We all saw the A320 that landed in the Hudson and how well behaved it was on the water. And there actually have FAA requirements for the airplane to stay basically level and not sink too fast so people can get out. And that would be much harder to do, with a C-17 configuration airplane than with a normal Boeing Airbus type airplane. Then one last thing I'll talk about is a lot of business jets have this configuration, much more so than airliners. Why is that? And the main reason why all the business jets look like this, well, not all of them, but most of them, is that in an airliner, there's a lot of room under the floor, right? The space between the floor and the bottom of the belly is pretty tall. So all the wing structure can go under the floor in an airliner, you don't even notice it. But on a business jet, there's much less space between the floor and the belly. And so if your wing spar goes through the business jet, it would make like a bump in the middle of the cabin. And one way to avoid that is to put the engines in the back, and then you can have the fuselage sticking in the front, and the airplane stays balanced. And so if you have this kind of configuration for a business jet, the whole cabin is ahead of the wing spar, so you don't have that bump. You have a continuous, comfy, roomy cabin all the way back. And then at the very back, you can have like a little cargo space or a toilet or something. But in general, because there's so little space between the floor and the belly in the business jet, they try to move the wing way back there. And one way to do it is to have the engines in the back, because then it balances the airplane. And there's a few other factors too, again, like all these things, but these are the main ones. Any other thoughts about this? Or questions? Let's see, there's just a couple more. So, when do you have to retire an airplane? And this actually gets, like I said, into what I actually do for a living, which is look at airplane, how airplanes deteriorate over time and then what you do about it. So there's a few factors to talk about. One is, as the airplane, and it's very similar for an airliner and a military airplane as to, our Cessnas and RVs and things. As an airplane gets older and older and older, basically it requires more and more maintenance. And you guys know that. It's at least as true for commercial airplanes and military airplanes as for small airplanes. And the maintenance gets more and more and more expensive. And at some point it just becomes so crazy expensive that you don't really want to fly very often, right? Most people who have, DC-3s and P-51s don't fly it like all the time, right? And another issue is that in a commercial airplane, you're trying to make money. And that, in part, that means being as fuel efficient as you can. So the older an airplane gets, the more and more, more fuel efficient competitors exist, and the harder it is to justify flying this old airplane that burns a lot of gas versus getting a new airplane that doesn't burn as much gas, right? At some point, paying for a new airplane is worth it because that'll pay for itself in fuel savings and so on, right? So just economically, at some point, it doesn't make sense to fly an old airplane anymore. But that's not the only reason. There are reasons why you have to retire an airplane at some point. So I'll get into those. So like I said, airplanes deteriorate over time. So metals, fatigue crack, and composites delaminate and so on. But that by itself is not bad. As long as you're doing maintenance regularly, as long as at least once a year someone's opening things up and looking for the signs of structural deterioration, you can catch these things and repair the airplane and and be fine. The tricky part, the scary part is, what if there are some phenomena that cause deterioration that you can't detect, right? In the damage tolerance rule, so the damage tolerance is the technical term for this idea of, basically what's your window of detectability between when some kind of deterioration becomes detectable by a maintenance person and when it becomes critical or dangerous, right? Like what's your detectable to critical for each piece of structure on the airplane? It's something we have to calculate. So that's what I do. Either that or testing towards that is what I do with most of my time at work. So what's your detectable to critical? For certain kinds of structure, that detectable to critical can be very short. And there are certain phenomena that happen late in the life of the airplane where the detectable to critical is very, very short. To the point where unless you're inspecting the airplane, unless you're tearing the airplane down between every flight, you're probably not going to catch it. So I'll give you one example. Fatigue cracking. So if you look at a piece of airplane structure, whatever hole has the highest stress, or whatever little place it's thinner, or some hole that got drilled a little more roughly, or some place where they didn't put the fastener in right, is probably what's going to fatigue crack first. So normally if you open up an airplane and you find a fatigue crack, there's usually one detail that's fatigue cracked and the rest is fine. And then you just repair that one place with a fatigue crack and you're fine. But what if over the life of the airplane, instead of one critical detail or one thing that wasn't built just right, or one place that sees a lot of stress, instead of that one place fatigue cracking, what if you have a whole lot of fastener holes that all see the same stress and they all fatigue crack just a little bit? So instead of having one crack that you can find and detect, you have a whole lot of cracks that are all too small to see, but in aggregate, they drop the strength of your structure below, what's safe. So in the late 80s, there was that Aloha accident that you may remember, where the top of a 737 came off, and that's basically what happened. It wasn't one single fatigue crack. It was lots and lots of very tiny fatigue cracks that were too small to catch in service, and that's called widespread fatigue damage. So the technical term for this phenomenon of lots of little fatigue cracks. And once we realized that was a problem, long story short, the FAA started requiring full-scale fatigue testing, which the manufacturers already did, but now it's required by law. Because there are ways to do analysis, probabilistic analysis, to figure out at what age, after how many flights, after how many hours, does the airplane start becoming susceptible to widespread fatigue damage. But now the FAA says, no, you have to do a test to make sure that you don't have widespread fatigue damage through multiple lifetimes. And none of the real airplanes are allowed to fly more than half the number of flights that are simulated in the fatigue test airframe. So we take so Boeing takes a 787 or Airbus takes an A380, they put it in this torture machine, and they fly many flights a day. So they bend the wings up, they pressurize the fuselage, they move the control surfaces, all those things. So they try to simulate a lot of flights. Each flight takes, it's in the order of several minutes. So in an hour, you should be able to do a few flights. And so over a period of several years, you've flown 2, 3, or 4 lifetimes, something like that. And you can be sure that you don't have widespread fatigue damage. And so none of the real airplanes can fly that long. And the outcome of this is something called the limit of validity. And the limit of validity is a number that the manufacturer and the FAA have to agree on that says, okay, given the data that we have, we feel confident that this airplane design is not going to experience widespread fatigue damage, lots of little cracks that are hard to detect, until this many flights and this many hours. And it's illegal to operate the airplane commercially after that many flights or that many hours. And if an airplane gets to that point, like, imagine, 40 years from now, maybe someone's flown a 787 to that limit, and they say, well, the airplane's still fine, I want to keep flying. The only way to extend the life is to get more data, right? The technical term for this is limit of validity. It's the limit of validity of your test data, of how much you know, like of your knowledge, right? To be able to feel safe about flying the airplane further, basically you have to take an old airplane and put it back in the torture chamber and simulate more flights, which the military does all the time. Like right now, Boeing's doing a life extension program on the B-1, where we took an old B-1 and put it in the fatigue test chamber, or in the fatigue test setup. And we've done it for F-15s, and other companies have done it for the other airplanes. So the only way to once you get to that, so that limit is when might you have, to summarize all this, the limit of when it's unsafe to fly the airplane anymore is at the point when you might start having some kind of deterioration phenomena that you can't reliably detect before it's dangerous. And the only way to know where that limit is, or to extend that limit, is to do a bunch of testing. And the only way to extend the life is to do more testing, to know that you have more data and you know that it's not going to happen for longer.
And you say you use a factor of safety of 2 on that?
The regulations in the FAA say that the real airplane can't fly more than half. Yeah. Although that's, during the development of the airplane, that's true. Afterwards, there's some negotiation about what the limit of validity is. Like if maybe the airplane has been tested to two lifetimes, but we've done a whole lot of lab testing of subcomponents and of new materials, and maybe there's a whole lot of other test data that's not the full-scale airplane, but it's all the potentially critical things in the full-scale airplane. And then during the life of the airplane, we get data from maintenance about how the airplane's doing. So we can take all that data and go to the FAA and say, oh, come on, we feel really good about going a little further. And the FAA tends to be pretty reasonable about that. So it's not a strict one half. While the airplane's new, so maybe for the first several years, it's half, but then as we start getting more data, we can talk. Yeah?
Do you test all the way to failure, or do you just set a goal and say, hey?
Oh yeah, that's a good question. No, after 2 or 3 or 4 lifetimes, testing is expensive, and we say, I think we have all the data that we need. And that's part of why in 40 years, the airlines might come back and say, the airplane's still fine, can we keep flying? Like, well, time to pay for that additional testing. And then we might test it to failure. So no, we don't. The airplane's still basically fine at the end of the test. Yes?
Is all the testing done by air, or is some done in a wind tunnel?
Oh, no, so the way you load, so this is a structural test that I'm talking about, and the way you load the structure, she asked if it's done in air, in the wind tunnel. You make an airplane, and you never fly it, you tow it over to the back of the factory, and you put it inside I guess you can really see it from there. It's basically a bunch of like scaffolding, and there are a whole bunch of hydraulic actuators and cables that connect to kind of sticky pads on the surface, and those hydraulic actuators pull the cables, and so the sticky pads on the surface deflect all the surfaces of the airplane. And then you're also pressurizing and unpressurizing the fuselage just with pressurized air. So you do it on the ground in a Jeep. What's that? Yeah, exactly. So a cyclic fatigue test. Yes.
What do you anticipate the multi-failure for composites?
Oh, that's a good question. I probably know too much to give you a good answer for that. But what I'll tell you is, so the mode of failure for metals is that kind of widespread fatigue damage. Composites don't fatigue crack. They have their own little problems. So what's going to be the thing in composite structure? So the question is, what's going to be the phenomenon that towards the end of the life might cause a significant drop in strength, but be hard to detect? And yeah, I have a few guesses, but I probably shouldn't share them. There are some academic papers you can go and search for to get your answer, but I probably shouldn't say any more about that. If you show me a blue Boeing badge, I can answer that. But other than that, I probably shouldn't. So sorry. Yeah, so do use strain gauges. We use some, but what Boeing actually does in practice, and Airbus does it too, is we actually make 2 test airframes. So one of them undergoes years of fatigue testing. The other one undergoes static testing. And for static testing, we use more extreme loads, right? So this load just simulates normal flights. But then we have another similar setup where we simulate higher G pull-ups and higher speeds and more extreme deflections, things that in practice don't really happen in flight. And then we do strain gauge the heck out of that airplane and see if each component is straining and bending and so on, and seeing the loads that we expected. And actually during flight test, we strain gauge at least one of the flight test airplanes to see if during flight the strains are what we expect. So we do loads validation that way too. Yes? So we'll test one airplane in fatigue, and that's all that airplane's ever going to do. And we test another airplane in static, and that's all that airplane's going to do. And there will be a few flight test airplanes. But since you asked that question, I can't resist but bring up an interesting story, which is, okay, anyone, who knows? Has anyone heard about the Havilland Comet crashes in the 50s? Good. Why did the comet crash? Anyone know?
Square windows.
Square windows. No. Well, that was part of it. So why did the comet crash? Part is it has square windows with high stress concentrations in the corners of the square windows. But the Havilland people knew about stress concentrations. They put a radius in the window. They fatigue tested it to make sure it wasn't going to crack. And then once the airplane passed the fatigue test, they started flying it commercially. So as someone who plans fatigue tests for a living, the comet crashed because they made a mistake in their fatigue test. They planned a bad fatigue test. And why is it? That's because of your question. What they did is they made an airplane just for structural testing, and they first did all the static testing, so they strain gauged it, and they bent the wings up to however many Gs. They overpressurized the fuselage like 2 atmospheres a whole bunch of times to show how strong it was. And once they were done showing how strong it was and none of it broke the airplane, they then did a fatigue test. And the problem with that is that when you overload a piece of structure, especially metal, you might plastically yield it, right? If you take a paper clip and you do this to it, you just change its shape. So through that static testing, they changed the shape very subtly. You can really see it with your eyes, but basically each of those square window corners was expanded a little bit from that overpressurization, so that during normal pressurization cycles, during the fatigue test, they didn't crack. Because they were basically a little bit bigger than they were supposed to be. So they were in a little bit of compression So the fatigue test airplane didn't see the stresses that the actual airplanes saw when they flew because the airplane had been, basically stretched to begin with during the static testing. So you have to have one airframe for static testing and one airframe for fatigue testing. If you take your static test airplane and do fatigue tests on it, you're not going to get good data. And that's why the Comet crashes, because they only did it with one airplane instead of two. And fun fact, most new airliners will go through a high blow test in the factory. We do overpressure it just a little bit, mostly as a check to make sure it all holds together, but it gives you a little bit of a fatigue benefit, just like the Comet static test. And I've heard some from the FAA say that they take each airplane before delivery and pull 2.5 Gs to kind of stretch the spars a little bit too, but we don't do that. Yes?
I know plastics, the longer a plastic is at high heat and in the sun, it becomes more brittle. Are composites the same way with today's composites?
So not just composites, but metals can have properties that change over time. And it depends on the temperature, and it depends on other things. But, again, this is one of those things where I know too many details to, too many trade secret details to give you a full answer. But the bottom line is yes, some materials change properties over time. And so if you're thinking about the longevity of your airplane parts, that's something you have to take into account. Sure. Yes?
Do you think computer simulations will diminish the requirements and needs for actual physical testing?
That's a very good question. Will computer simulations diminish the need for actual testing? The answer is yes. And there's a whole large group of people at Boeing, and I help out with some of that. Basically getting better and better at simulations and showing that the simulations get closer and closer to the real test results, showing that to the FAA so that the FAA lets us do more simulation and less testing. You always need at least some testing, but as computing power gets better and as we test more different kinds of things, as we take richer data, our computer models are getting better and we're moving towards less testing. And actually my director gave a whole lecture last year about this, so I feel fairly comfortable talking about this publicly. That there are a whole lot of technologies being put into place that are making our simulations quite a bit better. And we're in the process of convincing the FAA to let us do a lot less testing than we currently do. Yes?
I would argue really different. It's how well calibrated your model is.
Right. Yeah, it's how good is the model. Yeah, that's definitely one way to think about it. All right, any other? And I teach courses about this. I can stay in here for 40 hours to talk about airplane structure and fatigue and damage tolerance. So, on the one hand, don't tempt me, but on the other hand, I'll hang out here and you can ask me questions later. Go ahead, I'll take one more.
So, the reason I asked this question, like it sounds like this way is a little bit more specific. If you take a different airplane,
You mean a different, so if you take a different airplane, do the same fatigue test. A different airplane of the same model, like two 737s, or a different? Yes, there is quite a bit of variability. There's quite a bit of scatter. I can go to a machine shop, I can go here and ask them to make me a rectangle of aluminum and ask maybe 5 rectangles of aluminum that are as identical as you can possibly make them, and they will, and I'll go run fatigue tests on them, and they will fatigue crack at different numbers of lives, or numbers of cycles. They'll have different fatigue lives. And as a function of which material you're dealing with, and of how that material is machined, or holes drilled, or whatever it is, I can tell you not just about how long it's going to last, right, like the SN curve, the material property, but also how much scatter there's going to be. So all this fatigue work that I do is very much statistical. You're always looking at distributions, and you're looking at means, and do I care about the worst 5%, the worst 1%? Yeah, so I'm doing statistics all the time because, each one's going to be different. And each hole in a 737 is going to be different. And each two beams that are supposed to be identical are going to be different. And then, and people put airplane together in factories, and sometimes it's Friday afternoon, sometimes it's Monday morning. The quality is good, but it's not exactly the same every time. That's absolutely true. And that impacts the fatigue quite a bit. And part of fatigue testing is measuring exactly what that scatter is. All right, so I'll move on. And if you have any more questions about structures, you can come talk to me. Like I said, I can talk about structures for ages. So last couple of talks I'll talk about. One is flying cars. And this one, the answer has changed quite a bit over the past couple of years. So I started teaching my class at Boeing 3 years ago. And I would say, why aren't there flying cars? And the original answer to why aren't there flying cars, or why do flying cars not succeed in the market, is that a flying car is still an aircraft, and aircraft are expensive, right? A flying car is still going to cost as much as an airplane costs. And as you guys know, airplanes are expensive, and most people don't want to spend, $50,000 or $100,000 or multiple hundreds of thousands of dollars on their car. Some people do, but not a lot of people. So that's the main reason flying cars have not been a success so far. And the sharing economy changes everything. Once you have Uber and Lyft, you don't have to own the flying car anymore. A company can own the flying car, or an investor, or an rich individual, and they can share it. So once you have the whole sharing model, all of a sudden flying cars become not as crazy as they were like 3 years ago. And that to me, that's really the main thing that shifted us from flying cars, that's a crazy idea, to, well, you know, maybe. So as you know, if you wander around here, there's a lot of companies all working on electric vertical takeoff and landing, you know, flying cars. And once we get the airspace regulations and get them to communicate and get them to not hit each other and get them to fly autonomously, safely, and all that kind of stuff, you know, we could have flying Ubers. Uber certainly thinks we will. So that's kind of interesting. It's interesting to see how, you know, it wasn't that long ago. 3 years ago is not a long time in the big picture. But my answer to this question has totally changed from no way to, well, you know, yeah, maybe. So, you know, just to list a few different ones in case any of them are not here, you know, Airbus has a concept that they call pop-up, which is where you go in this little pod, and it has, you know, 4 propellers that will carry you around like an aircraft, and then set you down with these wheels, and then you can drive off to your destination, and then the 4 propellers can go pick up someone else and fly them. So that's kind of cool. And, you know, a company called Lilian made this really cool vertical takeoff and landing electric airplane, so it has fans built into the wings and the canards. You know, and that one's, you know, Aurora Flight Sciences flew a prototype flying car. Actually, I think Boeing bought that company in part because of that. And Vahana flew this one, and Airbus now partnered with them. And you have Cora, and you have Kitty Hawk. You know, there's a whole bunch of different companies all doing basically this kind of thing. And, you know, a few of them are here. And, you know, it's not on my slide because it came out a week ago, right? There's that, what's it called, that Black Fly opener one. I would have put it here if, you know, if it existed a week ago. But it just came out. So that's the... So we're now at 2:15, so that actually brings us to the end. So I'm not going to get into the bonus topics that I brought in after all, because we, you know, talked about various other things. But yeah, if you have any questions or other thoughts, or in case you want to talk about canards and flying wings, I'll be here. So yeah, thank you very much for coming, and yeah, enjoy the rest of Oshkosh. Thank you.